Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, so for our look into the sources today, we're zooming out.
Way out.
Way out, yeah, past the edge of our own galaxy, the Milky Way.
And we're focusing on our two closest and probably most famous galactic neighbors.
Right, if you're in the southern hemisphere, you just can't miss them. The large and small Magellanic Cloud.
There's so much more than just these beautiful patches of light in the sky, though. I mean, for centuries, they were guides for sailors.
And inspiration for poets, sure. But for astronomers, they represent something else entirely.
Oh, absolutely. For astronomers, these irregular dwarf galaxies are home to some of the most profound and honestly most frustrating mysteries in all of galaxy evolution.
And that's why we're looking at this today. Because this isn't just about another observation. We're talking about a massive, dedicated research program.
Monumental is the word. A 5-year program focused entirely on these two galaxies.
The whole mission here is to take what look like these abstract clouds of stars and gas, and turn them into a detailed, meticulous cosmic history.
And that's exactly what we're going to unpack. We're looking at the sources that detail this new astronomical campaign, trying to figure out what makes these two galaxies the ultimate cosmic lab.
And what are the core scientific puzzles that this huge data collection is really designed to solve?
Exactly. We want to give you the shortcut to understanding the secrets that are locked away inside the Magellanic Clouds.
So the starting point, the ultimate takeaway, really begins with just geography, or I guess cosmic geography, proximity.
Proximity is everything. In galactic terms, they are practically on our doorstep.
How close are we talking?
The LMC, the large one, is about 163,000 light years away. The SMC is a little bit further, around 206,000.
And just to give you some perspective on that, the next big galaxy, Andromeda, is what, over 2.5 million light years away?
Right. So this sheer closeness is what makes them so scientifically valuable.
Invaluable, because they give us a perspective we just can't get from inside our own galaxy.
Precisely. We can resolve individual stars with incredible clarity because they're so close. We can map out their entire structure, their stellar populations, the internal dynamics.
Without all the clutter of the Milky Way getting in the way.
Exactly. The sources call them excellent natural laboratories for studying things like galaxy evolution and star formation. And those are processes that are either completely hidden by dust in our own galaxy or just impossible to see coherently from where we sit inside the galactic disk.
Okay, so we have the perfect subjects.
Yeah.
Now we need the team and the tools. And this is a huge international project, but there's one institution really spearheading it.
That's right. This whole push is being led by a new research group at the Leibniz Institute for Astrophysics Potsdam, the AIP.
And a key person here is Dr. Laura Cullinane.
Yes, a postdoc at AIP. And her focus is really on the nitty-gritty details, the chemistry, the motion of individual stars within that bigger galactic picture.
And the project itself has this wonderfully grand name, 1001 Magellanic Fields.
Mercifully shortened to 1001 MC.
It does have a nice ring to it.
It sounds like an adventure, and honestly, the scale fits. The main goal here for Dr. Cullinane and her colleagues is to resolve individual stars. We're not talking about just blurry smudges of light.
No, this is getting down to the component parts.
Exactly. The idea is that if you can understand the detailed chemistry and the movement of, say, 500,000 single stars, you can piece together the whole life story.
The bigger picture. How these galaxies formed, how they've interacted with each other, how they've changed over billions of years.
It's like collecting billions of tiny stellar history books to write the complete biography of the clouds themselves.
You're turning an abstract cloud into a detailed family tree.
That's the mission. We're moving from just observing the symptoms of galactic evolution to actually understanding the mechanics behind it.
So let's get a bit deeper into this idea of them being a superior laboratory. I mean, why is it so much better than just studying the Milky Way?
Well, you know that analogy we sometimes use.
The one about being stuck in a foggy valley?
Exactly that one. Trying to map our own galaxy from the inside it's like that. You've got dust, you've got clutter everywhere.
Extinction, right. Just blocks the view.
Completely. But with the Magellanic Clouds, we get this This holistic view. We see the whole thing top to bottom. We can map their entire stellar populations without that heavy interference.
It's more than just the view, right? Their actual physical characteristics are different.
Oh, very different. And that's what makes them such perfect test beds. It's really about their gas content and, you could say, their maturity.
And the contrast with the Milky Way is pretty stark.
Absolutely. Two main things define them. First, they are way more gas-rich than we are.
Meaning a much higher fraction of their mass is just raw hydrogen and helium.
The pristine fuel for making new stars? Exactly.
So they have a lot of gas left in the tank waiting to be used.
They do. And second, and this is probably even more critical for testing our big cosmological models, they have a much lower metallicity.
Okay, so when astronomers say metallicity, we're talking about all the elements heavier than hydrogen and helium. Why is it so important that they have less of that stuff?
Well, low metallicity means the LMC and SMC have had less chemical enrichment over their lifetimes. Heavy elements are forged inside stars and then blasted out into the galaxy when those stars die, usually in supernovae.
So lower metallicity means a less mature or maybe a less efficient star-making system compared to our own galaxy.
Precisely. And that's what helps us test our models of galaxy formation.
How so?
Our big cosmological simulations have always kind of struggled with dwarf galaxies. A key problem is figuring out how chemical enrichment, that buildup of heavy elements, actually happens in these small, low-mass systems.
Because they don't have enough gravity to hang on to all the gas that gets blown out by supernovae.
Exactly. So the LMC and SMC, being both metal-poor and actively forming stars, they let us see star formation happening in the exact conditions that our theories predict dominated the early universe.
So we can watch how stars form when the environment is still relatively pristine, something we just can't do in the Milky Way's mature, metal-rich disk.
They're like living fossils of early galaxy formation. It's an incredible opportunity.
That context is invaluable. And within these metal-poor gas clouds, there are some specific spots that are they're astronomical showstoppers.
They really are. Cosmic extremes. In the Large Magellanic Cloud, you've got the Tarantulan Nebula.
Also known as 30 Doradus.
And our sources describe it as an extremely active star-forming region, which is, frankly, an understatement.
It's the most active region of massive star formation in our entire local group of galaxies, isn't it?
It is. It is an absolute engine room of stellar creation. It has some of the biggest, most luminous, most massive stars we know of. Some are dozens of times the mass of our sun.
And the fact that a relatively small, low-metallicity galaxy like the LMC can host such a monster star-forming region is a puzzle in itself.
It is. The radiation and winds from those newborn giant stars are just constantly sculpting the gas around them. Studying them helps us understand the absolute upper limits of star formation physics.
And the Small Magellanic Cloud, it has its own version of this.
It does. NGC 346. It's an open star cluster and nebula that's also actively forming a lot of high-mass stars.
So it's another real-time testbed.
But crucially, it's doing it in the even lower metallicity environment of the SMC. So we get to observe the same physics, but under slightly different, more primitive chemical conditions. It's a perfect comparative study.
And beyond these crazy star-forming regions, the clouds also contain objects that are, well, they're fundamental to how we map the entire universe.
You're talking about their huge population of variable stars.
Exactly.
These stars, specifically the Cepheid variables, are absolutely vital. There are standard candles for the cosmic distance ladder.
Because the relationship between how fast they pulse and how bright they truly are is very well understood.
Extremely well understood. So you can compare their true brightness to how bright they appear from Earth, and from that, you can calculate their distance with incredible accuracy.
And by extension, the distance to the galaxy they live in.
Precisely. And because the Magellanic Clouds are so close, we can make hyper-accurate foundational distance measurements to their Cepheids. Those distances then calibrate the entire cosmic distance scale.
The yardstick we use to measure the whole universe, all the way up to calculating the Hubble constant and the expansion rate.
Right. So detailed data on the variable stars in the LMC and SMC is bedrock science for the whole field.
It sounds like they're just constantly churning out stars and lighting up the cosmos. But you mentioned there's a kind of inconsistency to their activity level. It's not a smooth process.
And this is maybe the most fundamental question about their internal life that this 1001 MC survey wants to answer. The sources show that even though the clouds have stars of all ages, from very young to very old, the rate of star formation hasn't been constant.
It seems to happen in what they call episodic bursts.
Exactly. Episodic bursts. which suggests long periods of relative quiet, punctuated by these intense, spectacular firework displays of starbirth.
But what's pushing the on switch for those fireworks?
That is the core puzzle. Why the bursts? Is the gas compression that you need to trigger mass star formation coming from something internal, like complex gas dynamics within the galaxy itself?
Or is the trigger external?
Right. Is it the gravitational or physical interaction with the Milky Way? Or even just the frequent close passes between the LMC and the SMC themselves?
And the sources suggest that if the bursts line up with the times of close gravitational encounters, that would point very strongly to an external trigger.
Absolutely. A gravitational shock wave from a close pass can compress gas and kick off a huge wave of star formation. But to know that for sure, we need hard data. We need the precise ages and the motions of the stars that were born in those bursts to verify that connection.
We need to figure out who's pushing the nitro button that accelerates everything.
And that leads us perfectly into the instruments that are designed to find out.
Okay, so if the clouds are the perfect lab, you need the perfect tools. And the instruments for this are, well, they're pretty incredible, right? Down at the Paranal Observatory in Chile.
Oh, the hardware is state-of-the-art. It all centers on the VISTA Telescope.
VISTA, that's the Visible and Infrared Survey Telescope for Astronomy.
Right, but it's just been given this massive upgrade, a new instrument called Foremost.
4-meter multi-object spectrograph telescope. So a spectrograph.
Exactly, which is attached to VISTA. Let's start with VISTA itself, though. It's got a huge 4.1-meter primary mirror.
But its real specialty is its vision. It sees in the near-infrared.
And that near-infrared, or NIR, capability is just crucial. VISTA is the largest telescope in the world dedicated to wide-field surveys in the NIR.
Why is NIR so important for this?
Because it lets you see through the dust. Galactic dust particles that block visible light are, well, they're basically transparent to the longer wavelengths of near-infrared light.
So you're not just seeing the bright stars on the surface of the clouds. You're actually peering right into the heart of those star-forming regions, like deep inside the Tarantula Nebula.
Precisely. It lets them do an accurate census of stars that would be completely invisible in a normal optical light survey. It's essential for getting a complete, unbiased sample.
And the camera on this thing it's a monster. A 3-ton, 67-megapixel camera.
It's stunning technology. But Foremost is the new brain of the operation. That's the upgrade that takes all that light-gathering power and turns it into historical evidence.
A multi-object spectrograph. What does that actually mean?
It's a fiber-fed spectroscopic survey instrument, and the multi-object part is the real game changer.
Instead of looking at one star at a time.
Right. Instead of pointing at a single star to get its spectrum, Foremost has this complex robotic positioner that moves thousands of tiny little optical fibers across the focal plane.
How many targets could it hit at once?
It can collect light from up to 2,400 different objects simultaneously in a single observation.
2,400.
So it's basically doing 2,400 separate spectroscopic measurements in the time it would have taken older instruments to do maybe one or two. It's the only way you could hope to get a sample size of 500,000 stars in a reasonable time.
That just completely changes the logistics of a survey like this. So what's the timeline?
This is all happening right now. Foremost achieved first light back in October 2025. It's in its commissioning phase as we speak, getting everything calibrated.
And science operations are scheduled to start soon.
Second quarter of 2026. And here's the kicker, the thing that shows you how important this mission is. For a strict 5-year period, VISTA and Foremost are completely dedicated to this program. It excludes all other observations.
Wow. A 5-year block on a world-class telescope. That's an enormous commitment of astronomical resources.
It is, which brings us to the mission itself, 1001 MC.
The 1001 Magellanic Fields, co-led by Dr. Collinane.
The ambition is just staggering. The goal is to get the spectra of about 500,000 stars across the main bodies of the clouds, and just as importantly, way out into their faint outlying regions.
500,000 individual stellar life stories. So for someone listening, what's the really crucial data that the spectrograph gives you that you can't get from just a picture?
It gives you 2 revolutionary types of data. First, high-precision elemental abundances.
The star's chemical fingerprint, its birth certificate.
Exactly. And second, extremely accurate kinematics.
Which is its detailed motion, its travel history, its velocity toward us or away from us.
Let's drill down on those abundances for a second. When you say chemical fingerprint, which elements tell you the most about the history?
I assume things like iron are important.
Iron is key, yes, for overall metallicity,
Wow.
but also what are called the alpha elements, things like magnesium and titanium. The ratio of iron to these alpha elements is super sensitive to the history of star formation.
How so?
Because a slow, steady rate of star formation produces a different chemical ratio than a rapid, intense burst does. It tells you about the rate of enrichment, not just the amount.
And the kinematics, how does a spectrograph measure motion?
It all comes down to the Doppler effect. Light from a star moving toward us gets slightly blue shifted.
Its wavelengths get compressed.
Right. And light from a star moving away gets redshifted, its wavelengths get stretched. And you need a high-resolution spectrograph to measure those tiny shifts with enough precision to get the star's velocity down to, say, a kilometer per second.
So you get the star's life history from its chemistry and its current path from its motion. And Dr. Cullinane specifically mentioned measuring this data in the outskirts. Why is that so important?
Because the outskirts, the halos of these galaxies, are where the tug-of-war is most obvious. If the Milky Way is tidally pulling material off the clouds, it's going to strip the stars and gas from the edges first.
Those are the regions that are most weakly held on by the cloud's own gravity.
Exactly. And they're very faint, which is why you need VISTA's wide field and NIR sensitivity and FORMOST's ability to target faint stars so efficiently.
Her quote really sums it all up, doesn't it? She said the goal is to trace the effects of interactions between the clouds by analyzing the kinematics and abundances of their stellar populations, particularly in the outskirts.
That's it in a nutshell. The focus is on finding the physical scars left by these massive gravitational fights.
So this incredible new data set is really designed to test some of the biggest, most revolutionary ideas happening in galactic dynamics right now. For decades, we had a pretty comfortable story about how the Milky Way and the clouds were interacting.
We did. The old paradigm was that the clouds were ancient satellites. They had been orbiting the Milky Way for maybe 10 billion years. They'd completed lots of passes.
Which implied a long, slow history of coevolution.
A very long, slow dance. But the sources are clear that this long-held idea has just been completely challenged, and that's what created the urgency for 1001 MC.
What was it that shifted the foundation of that theory?
The shift came from the ESA's Gaia mission.
Gaia, which is just mapping everything with insane precision.
Insane precision. Its strength is mapping the positions and the proper motions, that's the sideways movement, of billions of stars. And that data, when you combine it with some older Hubble observations, it suggests something. Well, something revolutionary.
Which is?
That the clouds might be on their very first passage by the Milky Way.
Hold on. Their first pass. Not ancient satellites that have been orbiting for billions of years.
Exactly. They might just be newcomers, just arriving in our cosmic neighborhood for the first time.
That's a massive revision of their history. If they're new, it means all the dramatic effects we see, the star formation, the gas streams, all of that has to be the result of a fresh, violent, rapid encounter.
Not a slow, billions of years long orbital decay. That's the profound implication. If they're on a first pass, their relationship with the Milky Way has only just begun.
And that has to have huge implications for understanding our own galaxy, too.
Oh, massive. It changes our estimates for the total mass of the Milky Way. Because if the clouds are moving fast enough to just be passing through, our galaxy has to be heavy enough to have captured them only temporarily or to be pulling them into orbit right now.
Not having held onto them for eons. It affects our understanding of our own dark matter halo.
Absolutely. And the most dramatic piece of evidence for this interaction, whether it's old or new, is the huge stream of material we see being ripped away from the clouds right now.
The Magellanic Stream.
The Magellanic Stream. This enormous ribbon of gas that trails hundreds of thousands of light years behind the clouds, stretching down toward the Milky Way's south pole. And there's also the leading arm, which is material fling out ahead of them.
These things are just immense physical scars that show something dramatic is happening.
And their very existence immediately raises three competing ideas about how they were created, which is what 1001 MC is perfectly designed to test.
We need to figure out which force is responsible, because each one leaves a different kind of signature.
That's the challenge. Is it hypothesis 1, 2, or 3, or a mix of all of them? And the key to figuring it out is in the kinematic and chemical data from 1001 MC.
Okay, let's take the first one. Ram pressure stripping.
Ram pressure stripping is what happens when the clouds plow through the thin, hot gas that makes up the Milky Way's extended halo.
It's like a cosmic headwind.
A perfect analogy. The pressure of that headwind just pushes the gas right out of the dwarf galaxies, stripping it away, But crucially, this mechanism mostly strips away gas, not stars.
Because the stars are much more tightly bound by gravity.
Exactly. So if the Magellanic Stream was purely from ram pressure, you wouldn't expect to find many stars in it.
Okay, but then there's the second hypothesis, tidal stripping.
That's the purely gravitational pull of the Milky Way.
The galaxy's gravity just yanks material off the edges of the clouds.
Yes, and because it's purely gravitational, it affects both the gas and the stars, especially those in the outer regions where the cloud's own gravity is weakest.
So if a 1001 MC finds a lot of stars in the Magellanic Stream, and their motions show they're on these wide, high-velocity paths that follow the stream, that would be strong evidence for tidal stripping.
That is the core methodology. The kinematics of the stars act as the filter. Tidal stripping leaves a very specific kinematic signature. Ram pressure predicts fewer strip stars, and their motion would be more irregular.
And then there's the third hypothesis, which kind of complicates everything, the interactions between the LMC and the SMC themselves.
They're close enough that their own gravity is causing problems for each other. The LMC is much bigger than the SMC, and it's actively distorting its smaller companion. Some models even suggest the stream was created mainly by the LMC ripping material off the SMC.
That seems like the hardest one to untangle. How does 1001 MC solve that?
This is where the chemical abundance data becomes your second filter.
Chemical tagging.
Right. If you find a star in the stream that has the low metallicity chemical fingerprint of the SMC, you know it came from the SMC. Then you look at its motion. If its path suggests it was flung out during a close pass with the LMC, you know that interaction was dominant.
But if a star with an LMC fingerprint is on a path that clearly follows the Milky Way's tidal forces, then the Milky Way is the main culprit.
It's an astronomical forensics investigation, and you need the chemical tags from 500,000 stars to get enough data points to separate these different effects.
And this all ties back to that question of the episodic star formation.
Yeah.
What triggers the bursts?
Exactly. The survey gives us the tools to finally connect those two phenomena. We can figure out the age of a group of stars from their chemistry and life cycle stage, and we can correlate that age with the history of interactions.
So you can ask, did a burst of star formation happen right when the clouds were making a close pass to the Milky Way? Or when the LMC and SMC were closest to each other?
That's the key. If the stars born in that burst are kinematically linked to material that was just compressed or flung out by a shock wave, that's a strong argument for an external trigger.
And if they're just randomly distributed, it points to internal processes.
Right. And finally, all this ties into understanding the chemical evolution and what are called metallicity gradients across the clouds.
The abundance data doesn't just tell you if a star is metal poor, it tells you how those elements are distributed.
A metallicity gradient just tracks how the concentration of heavy elements changes as you move from the center of a galaxy out to its edge.
And typically you'd expect it to be highest in the center and then drop off.
Generally, yes. And the steepness of that gradient tells you about the history of gas flow and mixing. If galaxy has been constantly stirred up by interactions, the gradient will be shallower, the elements get spread out. If the gas stays put, the gradient will be steep.
So the chemistry of the stars actually reveals the plumbing system and the mixing efficiency of the galaxy's gas. That's a huge leap.
A massive leap in our understanding.
So someone listening might be thinking, okay, but we've known about these clouds forever. We've pointed huge telescopes at them for decades. Why is this survey the one that's going to crack it?
That's a really good question, and the answer comes down to one word: spectroscopy.
Because all those other big surveys, VMC, STEP, SMASH, OGLE, they were mostly doing photometry.
Overwhelmingly. And photometry is great. It gives you brightness, it gives you color, it can track changes in brightness over time.
It gives you a beautiful, detailed map.
A beautiful, but kind of flat map. It tells you what a star looks like and where it is. It does not tell you two absolutely vital things.
What it's made of and how fast it's moving toward or away from you.
Exactly. And the official European Southern Observatory documentation for Foremost says it directly. It points out that there is a pronounced lack of spectroscopic observations across the range of stellar populations and substructures of the Magellanic Clouds. That lack of spectral data is the scientific bottleneck.
So why does spectroscopy breaking the light down into its component wavelengths? Why does that change the game so much for these specific questions?
Because it's the only way to measure the tiny Doppler shift you need for kinematics, and the only way to see the absorption lines that tell you the elemental composition. And the quality has to be extremely high.
You can't just do low-resolution spectroscopy.
No, because that might give you a rough idea of total metallicity, but it's not good enough for the technique they're relying on, which is chemical tagging.
Chemical tagging, it sounds like a forensic technique.
It is entirely forensic. Stars are born from huge clouds of gas. And that gas cloud, at the moment it collapses to form stars, it has a unique, uniform chemical signature.
Its specific blend of iron, oxygen, and so on.
Right, which depends on which supernovae enriched it right before it collapsed. So every single star born from that cloud is a chemical sibling. They share an identical chemical fingerprint.
And they keep that fingerprint for their entire life.
Yes. So even if those siblings get thrown to opposite ends of the galaxy by gravitational forces over billions of years, their elemental abundance ratios stay the same.
So by analyzing their chemical fingerprints with high-resolution spectroscopy, you can prove that two stars that are now thousands of light years apart were actually born together.
That is the profound part. You can reconstruct the original birthplace of populations that were scattered by the Milky Way's influence.
And previous spectroscopic surveys just didn't have the power to do this.
They lacked the sheer volume of targets and the high resolution needed for this kind of detailed chemical analysis across such a huge population. They could tell us the clouds were metal poor, but they couldn't reliably do this tagging to trace where stars came from.
So the advantage of the 1001 MC is really threefold. The sheer number of stars, the wide area it covers, including the outskirts, and the high resolution of the data.
That combination is what makes it revolutionary. The ESO documents describe it as allowing for a comprehensive study of the kinematics and chemistry of a large number of stars at different evolutionary phases and with a wide spatial distribution.
So getting the depth of chemistry and the breadth of kinematics across the entire system for the first time.
Exactly.
So what does this mean for that Gaia data? Can 1001 MC actually confirm or deny the first pass idea?
It can provide the final critical piece of confirmation. Gaia measures the proper motion, right? The sideways movement across the sky.
But to know if something is truly bound to the Milky Way or just flying by, you need its full 3D velocity.
You do. And you're missing the radial velocity, how fast it's moving toward or away from us. Foremost's high-precision kinematic measurements provide exactly that missing piece.
And once you combine those two velocity components, you get the true 3D space velocity.
Which is the ultimate test. It tells you their orbital energy and whether they're gravitationally bound to the Milky Way or if they really are just newcomers passing through.
Which brings us back to the ultimate goal. This isn't really just about the LMC and SMC.
Not at all. It's about refining our knowledge of how all galaxies evolve. The Magellanic Clouds are our best, and maybe our only, opportunity in the local universe to study the life cycles of these gas-rich dwarf galaxies in such detail.
To see how they form stars in metal-poor environments, how they move gas around, how they interact, and how they evolve under these huge external forces.
This dataset, when it's complete, is going to be the bedrock for modeling dwarf galaxy evolution and for testing our big cosmological simulations for decades.
It promises to finally resolve these decades-long arguments over their history and the powerful forces that are shaping those incredible Magellanic streams.
It's an amazing project.
Wow. Okay, so this is a genuinely monumental project.
It really is.
So just to sort of wrap up the main points here, we're talking about a 5-year dedicated program
Using the foremost spectrograph on the VISTA Telescope,
to get the spectra of 500,000 stars.
which gives us their chemistry and their motion. The two things we were missing.
And this spectroscopic power is what's going to let researchers finally test these huge new ideas, like confirming or denying the Gaia data that suggests the clouds might be on their very first pass by the Milky Way.
And crucially, using that chemical tagging and motion data to finally figure out what created the Magellanic Stream, whether it was tidal stripping, ram pressure, or the clouds fighting with each other.
So by the time this is all done, astronomers will have the most comprehensive, detailed, high-resolution spectroscopic data set ever put together for dwarf galaxies.
And that data is essential for finding real answers about gas mixing, star formation bursts, and rewriting the history of our closest galactic neighbors.
Okay, so for our final thought for you to ponder, we spent a lot of time on this revolutionary idea that the Magellanic Clouds might be on their very first pass.
Meaning their gravitational interaction with the Milky Way is only just beginning?
So If that first-pass hypothesis turns out to be true, if the clouds have only recently encountered the Milky Way's massive gravitational and gaseous halo, what does the already vast and dramatic appearance of the Magellanic Stream tell us?
It implies that the forces of gravity and ram pressure are so incredibly potent that they don't need billions of years of slow, gradual work. They can rip material off a galaxy and stretch it across hundreds of thousands of light years in what is, cosmically speaking, a brief moment.
The streams aren't the result of a slow bleed over eons.
No. They are the evidence of an unbelievably powerful, almost instantaneous cosmic collision. And the 1001 MC spectra will be what tells us just how violent that first encounter truly is.